In this video, we're going to derive the backpropagation algorithm for training neural networks, that is, for learning the weights. So our objectives are to find a method for learning the weights in a neural network. We're going to do so by applying stochastic gradient descent, and this involves finding the gradients of squared error loss with respect to the weights. So the backpropagation algorithm uses stochastic gradient descent to train the weights. So we have a network which has one hidden layer and an output layer and then the input layer. Now we've denoted the hidden and the output layers with these open circles, and those represent the actions of the activation function. H1, for example, is going to be the activation function applied to W11 times X1 plus W12 times X2 plus W1M times X1. We can in general write the outputs d hat q is the activation function applied to the weighted sum of the previous layer outputs, the h's, and similarly the h's are the activation function applied to the weighted sum of the inputs. Now in the derivation we're going to do today, we're going to use an activation function of 1 over 1 plus e to the minus z. So stochastic gradient descent is going to take our n training samples, features xi from xi1 to xim, and then we have corresponding labels di, and we'll assume that we have a total of capital N of those features and labels. We're first going to initialize the w's and the v's to some guess, and then we're going to iterate. So within each iteration, we're going to pick one of the training samples at random. We're going to use that sample to compute the values of the hidden layer and the values of the output layer. And that allows us to update the weights. So our update is going to be create the new weight in terms of the old weight at time t minus a step size times the gradient of the cost function with respect to the weight. And similarly, we'll do for W. We'll update the weight, the new one being the old one minus a step size times the gradient of the cost function with respect to the weight. The essential task we have before us right now is to find these gradients. And the method that we use to find the gradients are to apply the chain rule. We'll do this for the squared error loss, or loss as a function of the weights at the different layers, can be written as the sum over all the training samples, and then we're going to throw in a factor of 1/2 here to simplify things when we differentiate with respect to the squared error, and we'll sum over all the output nodes of the difference between the predicted label and the actual label. Now we'll call this sum over all the output nodes for the ith training sample, we'll f sup I. So remember, stochastic gradient descent is operating on this loss for a particular training sample. So we'll apply the chain rule and find the gradient of the cost with respect to the weights in the output layer, the v's, by writing that as the gradient of the cost with respect to the output labels times the gradient of the output labels with respect to the weights. So using this squared error loss, I take the derivative of this with respect to v sub k comma l, and since v sub k comma l is associated with the kth value of the output labels, instead of summing over q, I'm just going to look at the kth one. And so differentiating, I have 2 times 1/2, that goes away, and then I have the parentheses here times the derivative of the activation function with respect to its argument times the derivative of that argument with respect to v. So recall that the activation function we're using in this example is 1 over 1 plus e to the minus z. So if z is large and negative, that's going to be 0. If z is large and positive, it's going to be 1, and it crosses 1/2 when z is equal to 0. So clearly the derivative is going to be 0 when z is large and negative, and 0 when z is large and positive, and takes the maximum value when z is equal to 0. So we can take the derivative of this function, and we have 1 over 1 plus e to the minus z squared times e to the minus z, and we can rewrite that as 1 over 1 plus e to the minus z times the quantity 1 minus 1 over 1 plus e to the minus z. And the reason we're factoring it this way is because that leads us to a really simple form of sigma of z times 1 minus sigma of z. Remember, sigma is the output of that particular node at that layer, so this is the output times 1 minus the output. Now in this particular case, we've got sigma prime of the sum n equals 1 to p h I n v k n. This is the input to the activation function for the kth predicted output label dik hat. So sigma of this quantity times 1 minus sigma of that quantity, this is di hat sub k times 1 minus di hat sub k. So the derivative, sigma prime, takes a very simple form, and the partial with respect to v is also simple here because this is just a weighted sum of the v's, and the derivative is just going to be the corresponding value of h that's applied to this particular v. We've shown now that the gradient of the loss with respect to the weight v sub k comma l is d hat I sub k, the predicted label at the kth output, minus the true label associated with the kth output, times d hat ik times 1 minus d hat ik times the corresponding output of the preceding layer. So this gradient takes a very simple form, and that leads to a very straightforward update for the weights. The weight at the next time interval is equal to the weight at the previous time interval minus the step size times delta ki, which I'm calling an error associated with the output, and then times hil, which is the layer input. So I'm calling this an error because if d hat I differs from di, then there's going to be an error in the label, provided that d hat I is neither 0 nor 1. In other words, the input to the activation function is not large and negative, and it's not large and positive, then we're going to have a non-zero term associated with delta ik. So this delta is going to be 0 when either the label is correct or when we're at one extreme or the other with z, or when we're at one extreme or the other with the input to the activation function. And we can use a very similar approach to find the gradient of the loss with respect to the weights at the input layer, although we're going to use a chain rule with one more step in it. So in this case, we're going to sum over the labels and the outputs. We take the derivative of the loss with respect to the output values, and we're going to take the partial derivative of the output values with respect to the hidden node values, and then we're going to take the derivative of the hidden node values with respect to the weights that feed that hidden layer nodes. While we know that the derivative of the loss with respect to the qth output label is just the predicted label minus that true label, and so that takes care of this first term, and we'll look at the second term, the partial of the output label with respect to the values output by the previous layer. So again, we're going to be taking the partial with respect to sigma, and that's going to be the derivative of sigma, sigma prime, times the derivative of the input to the activation function, which is just a simple linear sum. So when I differentiate this sum with respect to h sub m sup I get v q comma m sup I. Then I have the derivative of the activation function evaluated at that argument, and again, as we did on the previous slide, to be the product of the predicted label times 1 minus the predicted label. So that takes care of the second derivative, and now we've got to find this third derivative. Since we're differentiating the output of the first layer with respect to the weights in that layer, we're again differentiating with respect to sigma, the activation function, so we're going to have the derivative of the activation function times the derivative of the argument of the activation function with respect to w, and that is again a sum, a weighted sum over the w's, so that's just going to be the corresponding x that's applied to this particular w, which in this case is xj sup I. So the derivative of the activation function with respect to its argument, remember that's going to be sigma of z times 1 minus sigma z, but in this case sigma of z is the output of the hidden layer, in other words him times 1 minus him. So we can put this all together, plugging these terms in, and I'm going to have a sum over q of these various terms that we discovered, the derivative of the loss with respect to the output in this first parentheses. Then we're going to have the derivative of the output label with respect to the input from the previous layer, which is dq hat 1 minus dq hat vq comma m. And then finally, we have the derivative of the hidden layer with respect to the input weights to that layer, and that's hm times 1 minus hm times xj. So we're going to group this constant in front here when we sum over q. We're going to call that gamma sub m sup I. So this gives us a very simple update for the weights in the initial layer, the input layer, and that is the weight at the next time instant is the weight at the previous time instant minus the step size times this gamma term, which is a backpropagated error of sorts, times the input to the corresponding layer, which are the input features xji. Okay, that was a lot to wade through to get to this result, so we're going to now summarize. And the basic idea is that this backpropagation algorithm at the end of the day involves some very simple computations. And the way it goes is we're going to initialize our neural network with some initial weights in the input layer and the output layer. And then we're going to iterate. And for each iteration, we're going to use SGD. So we're going to pick a random training sample, index that as I sub t, from the set of training samples that are available. Then we're going to do a computation running that training sample forward through the net. In other words, we're going to use the input, our current weights, to find the output of the hidden layer, hm, at this training sample, and to find the predicted label at the qth output for this training sample. Once we have these values, we can now do the gradient updates. And our updates proceed backwards. We're going to update the weights at the output layer, these V's, by first of all finding this error term delta K sup IT, which involves the difference between the predicted label and the true label, and that leads us to updating the V's. And we can take this error term and propagate it backwards to find the corresponding error terms for the previous layer. So given the delta K at IT, we can find gamma M IT. As I've indicated here, it's just a sum Q equals 1 to cap Q delta Q IT, the weights at the output layer at time t, times the output of the hidden layer times 1 minus that corresponding output. And that leads us to update the weights at the input layer, where the next weight is equal to the previous weight minus a step size times this gamma factor times the input associated with that particular weight. One can do variations on this. It basically follows the same pattern if you want to consider other activation functions, or if you want to look at networks with more layers, the updates follow a similar pattern as one goes, both with taking the training data and first propagating that forward to find all the intermediate variables in the network, and then propagating the errors backwards to do the gradient descent updates. Now the cost or the loss associated with the neural network is a non-convex function of these weights. So that means at best our gradient descent is going to converge to a local minima. And one can do different things like start from different initial conditions for the weights and pick the one that works best. There's also a number of empirical tricks that can be used to improve convergence performance, such as batch SGD, where rather than iterating on a single training sample at a time, you iterate on groups of training samples. And you can also normalize these training samples in different ways. And these are methods that in some cases do accelerate convergence. Of course, one can also derive a gradient descent update with a regularization term on the weights. So developing an algorithm for training or learning the weights in a neural network is a fairly straightforward procedure, as we've seen here, though one needs to exercise care with the details. However, many of the other aspects of neural networks, like how many hidden layers to use, how many nodes per hidden layer, what sort of batch or normalization technique one uses, those end up being much more of an art than a science.